Hello, welcome to my lectures on mechanical design and applications of high temperature materials. I'm Nas Ghonim, Professor of Mechanical and Aerospace Engineering at UCLA. In this lecture, I'm going to cover an important application of material selection and a process that was invented by Professor Mike Ashby that has kind of a coarse way of choosing in between different alloy systems and ranking materials for several applications. What we will do is we'll just focus on the important properties relevant for high temperature mechanical design as we have done in the previous course on power transmission. We use the Ashby charts for deflection and for strength, but here we're going to use different types of properties that are really relevant when you couple heat transfer and also the strength and the rigidity of the material. So in this lecture, I'm going to cover a number of material selection processes using the Ashby charts. And the first process or the first property that we will look at is the thermal conductivity. And as we know, the higher the thermal conductivity, the larger the heat flux that can go through the material. So if you look at the basic relationship between the heat flux Q and the temperature gradient, which is the difference in temperature T1 minus T2 divided by a thickness of the sample X, then we find that the heat flux is proportional to the temperature gradient and the proportionality constant. In this case, we call it lambda. In other situations, it's called K, but here lambda is the thermal conductivity. So thermal conductivity is a measure of how much heat flux can pass through a sample given that we fix a temperature gradient across this sample. So in a way, the temperature gradient is a way to distort thermally the material to cause thermal strain. So we would like to have this within a desired range, and therefore the higher the thermal conductivity, the higher the corresponding heat flux of the material. So in this case, what we will do is we will look at other properties. As we said, that the thermal conductivity is for steady state heat flow through the sample. So as you have continuous heat flow, you establish a temperature gradient across the sample, and therefore the conductivity will control the steady flow of heat. When we have designs that actually are considering operation where the temperature rises on and off, for example, the jet engine combustion chamber, it is fired on for a period of time and then it gets fired off. So during this on and off, ramp up, ramp down time, the heat has to be dissipated in a transient fashion. So just kind of the temperature is going to increase and then it will settle at some value and then it will decrease again. So the transient going up and down is not controlled. This kind of behavior is not controlled by the thermal conductivity, but is controlled by another material property called the thermal diffusivity. So if we look at the thermal diffusivity, it is defined as the ratio of the thermal conductivity divided by the product of the density times the specific heat at constant pressure. So the specific heat at constant pressure has the units of joules, which is energy, divided by kilogram, so it's energy per unit kilogram per unit Kelvin. And therefore, we can look at the product of rho Cp as the volumetric thermal conductivity of the material. So if you have 1 meter cube of the material, this is the volumetric specific heat. rather. So if you have 1 meter cube of the material, the rho C sub P would represent how much heat can be stored in that 1 meter cube of the material. So the diffusivity alpha A is the ratio of lambda over rho sub P. So if I take lambda divided by A, then we would get rho times C sub P. So it turned out to be that rho times C sub P is dependent on the density of the atoms of the material. And therefore, for most materials, the product of rho times C sub P is very similar. The only exception, as we will see, is micro-engineered materials such as foams, for example. The next property that is important is called the thermal shock resistance. And the thermal shock resistance is defined as the gradient, the temperature difference across a sample in units of Kelvin that causes fracture. So if we just take a piece of material and quench it from one side and then impose a temperature gradient or a temperature difference, as that temperature difference increases, you get to a point where the material will crack. So this is important in very rapid cooling cooling or heating of material samples. The next property that is important at high temperature is creep resistance. And we've seen that in most cases, the determination of the strength of the material is not based on instantaneous loading, but the material is really weaker if the loading is continuous and that the material is subjected to high temperature at the same time. This condition is the creep condition, which is called viscoplasticity. So the material kind of continuously expands until it eventually ruptures. So we use the term creep rupture. So I bring it to a design application. If we look at turbine blades, for example, the turbine blade is inside a housing and there's a gap and it rotates very fast. So we need to have a gap in here. But as the temperature increases, then the blade will expand and then it will expand continuously by creep until it hits the housing of the turbine that's for the engine, and that is catastrophic. So in this case, creep, although we haven't lost the strength of the material, but it elongated so much that it is not anymore functional. So there are limitations of the creep strain that we can consider. So in this case, the property we look at is the creep rate. This is, for example, this is epsilon versus time. So if you put a force on a sample, then the force will cause deformation, like a strain. U is the displacement. So the displacement rate is the strain. So this should be epsilon and not epsilon dot. So epsilon is equal to displacement rate over L, the length. And the strain itself is characterized by 3 regimes: primary, and then steady state. The slope here of the steady state regime is constant. Epsilon dot is the slope of this curve. And then the slope becomes accelerating until we get rupture at this X point. So this is at temperature T1. If the temperature increases, the process accelerates faster. And if it increases even faster, then we get the process to increase in the deformation rate until you get rupture much faster. So the important property is the slope of this steady state. Most deformation occurs in steady state, although in some designs we're going to also consider the transients when we have cyclic plasticity. But here, if you have a steady state creep rate, is generally described by a parametric form in the finite element codes as a constitutive equation. And that form has four constants: epsilon dot 0, sigma 0, it's like a relative strength of the material, strain rate exponent n here, or the stress exponent n, and that is usually greater than 1, could be 2 to 10, depending on the material, and an activation energy that describes the temperature sensitivity. So with these four constants, we are able to describe the creep rate. If we have this equation, we are able to describe the deformation, at least in uniaxial, and then as we will see later in the course, how we use such relationships in multi-axial loading. The next key property is dry corrosion, which is a chemical reaction of the solid surface with dry gases. And as I mentioned, this is important for the interaction between the gases or the coolants, either the gases that generate the heat, as in the combustion chamber itself, or the coolant on the other side that cools the surface. So the material is like a sandwich. From one side, we get combustion or energy source. From the other side, we get a coolant. And the coolant and the combustion, both of them can be either gases or liquids. So in this case, we can have corrosion. So if we consider only gaseous corrosion, then the situation is a little bit simpler, because the rate of change of the thickness of the material is governed, or the amount of corroded material or removed by gases is described empirically by two constants. One is the oxidation rate constant, K sub P, which has units of meter squared per second, very similar to the thermal diffusivity, same units. And another constant is the activation energy for dry corrosion. So once we know these two parameters, we can integrate this equation, and we get a relationship that x squared is a constant times the time. So for a given temperature, this K sub P times exponential of minus Q over RT, all of this will be a given constant, and then the x squared will be proportional to the time. So this behavior, we call it parabolic corrosion, because it's a parabola. S squared is proportional to T, and therefore if I want to find the thickness that's corroded or removed, it will be proportional to the square root of T. So it rises quickly, and then it slowly kind of levels off as time goes on. So as you can see here, there are two properties that are proportional to the square root of T. One is heat diffusion, so the diffusion of heat through the material in a transient. And the other one is the corrosion rate of hot gases through the material is again proportional to the square root of T. So if we continue now for the properties that we have used, so if I look to summarize again, we have thermal conductivity, lambda, we have thermal diffusivity, A, we have thermal shock resistance, which is a delta T, we have the creep resistance, described by the slope of the creep curve, epsilon dot. We have the oxidation resistance described by this oxidation rate constant K, and energy Q, activation energy Q. So with that, now we turn our attention to Ashby charts that can classify the materials for various design applications depending on these properties. The first chart we look at here is a chart that is a relationship between the thermal conductivity and the thermal diffusivity. This relationship is either to tell us how fast the heat will go through a material, or the maximum heat flux that the material can take. So the lower the thermal conductivity, the lower the heat flux. The higher thermal conductivity, the higher steady state heat flux. The higher the diffusivity, the faster the heat is going to go through the material. So there is the ratio between lambda over A. We discussed it. This ratio is the volumetric specific heat. So the materials, this is 10 to the 5 volumetric specific heat, and 10 to the 8 and 10 to the 7. So you can see 10 to the 6, 10 to the 7. So you see most materials, which is very surprising, lie along one line, which is approximately somewhere between 10 to the 6 and 10 to the 7. The only exception, as I mentioned, is engineered materials like foams. And foams here have very low thermal conductivity, so they cannot really sustain a very high heat flux. But at the same time, they have higher, relatively higher diffusivity, so they can pass the heat very quickly. And that can be important in some design applications. And then you can see the lines, the steady state lines in here. The higher the lambda over A, the more heat flux you can have. So you have, for example, copper alloys would be the best for conducting heat in steady state. And then aluminum is lower, zinc is lower, tungsten is not so good. And then you get nickel is not even comparable because the thermal conductivity is lower. And the units here in watts per meter K. So anything above 100 is a good thermal conductor. Anything below 100, then we have to kind of think twice on using it for high heat flux applications. So that's why copper and copper alloys are used as heat sinks for many applications, including even microelectronics. And as we consider transients, the lambda over square root of A would be a line that we can choose from, indicating that the foams would be a good choice in that case when we consider transients. The next chart here is the relationship between the thermal expansion and the thermal conductivity. And as we know, the thermal expansion coefficient is the amount of microstrains divided per unit degrees Kelvin. So if I put 1 degree Kelvin as on different temperature difference on a material, and then I measure the delta L over L, that will give me the strain, and convert this to microstrain. 1 microstrain is 10 to the minus 6. So most materials will give us maybe a few microstrains per degrees Kelvin. Some materials expand a lot, so you have 100, 200 microstrains. Some are lower. So the more expansion the material will have, the higher the thermal strain mismatch, because the strain is alpha times delta T. That's the thermal strain. So if you have a higher alpha, then you can have a thermal strain. But that doesn't mean that you have a stress, very high stress, because the stress depends on the modulus. So strain-wise, we can have high strains if we get a high coefficient of thermal expansion. And at the same time, if we consider the ratio to the thermal conductivity, it can give us a measure of the amount of microstrains that can be inducing a strain mismatch. So the thermal conductivity is on the horizontal, the thermal expansion on the vertical. So you will see now, if we look at all the metals here, very interesting, the microstrain is between 10 to 20 to 30 in this range. So they are limited in their expansion. If you look at ceramics, it's well below 10. So you have, for example, tungsten carbide is a few, 4, 3 or 4, glasses and so forth are kind of low. So these will have lower strains, and these will be a little bit higher strains. And the thermal strain mismatch is described by this ratio lambda over alpha. So the lower the alpha, the higher this ratio, and therefore you get the lower thermal mismatch strains on the right, and then higher thermal mismatch strains on the left. So the worst in terms of giving us the largest mismatch strain are the foams, polymers, elastomers, and these are usually not used in high temperature applications. And the best are given by this boundary here, where we have aluminum nitride, tungsten alloy, silicon carbide, and technical ceramics. So the ceramics are quite good in this regard. The next property that we look at for design is the thermal stress. So we mentioned the strain, but in a lot of cases the component is designed not for the strain, but is designed for the stress. So for the stress, we have to get into the modulus, because the stress, delta sigma, is alpha times delta T times the modulus of E. So the stress per unit Kelvin is alpha E with a constant. This constant depends on the constraint. So for axial is 1, for biaxial is 1 minus nu, and for other conditions, for triaxial is 1 minus 2 nu, where nu is the Poisson's ratio. So this alpha, the product of alpha times E, is roughly the stress per unit degrees Kelvin that you put across the material. Very simple. So if you have a low value, like 0.01, this is low thermal stress. If you have a high value like 10, this is pretty high thermal stress, because usually you have a delta T of several hundred. So if you have 200 degrees times 10, that gives you 2,000 megapascal. That's will fracture anything. Here, if you have 1 times 200, you have 200 MPa generated along this line. So if you look now above the 1 line, you get the metals. So you get the zinc, aluminum, copper, cast iron, steels, and so forth. Luckily, the strength of these materials are high, so they can take the stress. Now we can look now at the alumina and silicon carbide and tungsten carbide. They are closer to the 10 line, and their strength is lower. So these are not so good as far as the thermal stress is concerned. On the other side, if we're looking for applications that the thermal stress is very low, then we would consider elastomers, polymers, and so forth. But these are materials that we are not using in most high temperature applications. What next property that we look at is thermal shock, and the thermal shock is not for steady operation. As I mentioned before, we will consider both steady state and transients. In a transient, you can have a system that is fired up very quickly, and when it's fired up very quickly, the temperature would rise, but the material will be cooled at the same time. So if the rate of cooling is very high, we can take care of the temperature rise. If the rate of cooling is low, then the temperature rise is going to induce possibly fracture of the material. So this is during the turning on a device, for example, like an engine. Therefore, we need materials that do not crack during that transient period. So the cooling, the rate of cooling is important during the transient period. And therefore, we can describe this thermal shock resistance by a measure which is the delta T that causes cracking. So 10 degrees can cause cracking, 100, 1,000, and 10,000. However, since we have to consider cooling, the speed of cooling, then instead of delta T, we would use a parameter that's called B times delta T, where B is the BO number, and the BO number is the ratio of convective to conductive cooling. So if we have very high conduction, the BU number will be small and it will be tolerant to thermal shock. Because B is small, then you can take a higher delta T. If the BU number is large, then you're limited to the delta T that can cause fracture. So the stress is alpha E delta T. This is stress divided by a constraint factor C. And if we just want to have delta T that causes fracture, then we have sigma, which is the fracture strength, times C divided by E alpha. C is 1, then that would be a formula for delta T. But if we consider cooling, then we have to multiply by this BU number, and that is kind of the way that Ashby constructed this chart. Took the fracture strength divided by alpha E, and then you can see now the materials. They all lie between the 100 and 1,000 range, and the metals are right here. The zinc and aluminum alloys, magnesium alloys are right here. The steels are up there, so steels can take more. They're more resilient. So if you go back up here, this is more resilient, more thermal shock resistance. If you go down to the value of 10, for example, then you're talking about low thermal shock resistance. So looking at it, then we can ask maybe some interesting questions. So it's sort of like a quiz. So let's ask this. What do you think would be the material that has the highest ever thermal shock resistance in the world? What kind of material would it be? Well, if we look at the chart, there's a material called Invar, which is an alloy made between iron and nickel. And you know, in Switzerland, there are Swiss watchmakers, and it's very important to have watches that have very high precision. So there was this physicist, Dr. Golem. He developed an alloy that's a mix between iron and nickel. And sure enough, when the nickel content is about 36%, then the thermal expansion coefficient of that alloy becomes very, very small. So instead of 10 to 20 to 30 ppm per Kelvin, ppm is parts per million per Kelvin, instead of 10 to 20 ppm per Kelvin, he obtained a fraction of 1, like maybe 0.6, 0.7, which is a huge reduction in the thermal expansion coefficient. So the Invar alloy, if you make a watch, then it will be precise within a good temperature range because there is no significant thermal expansion. So as we mentioned, the thermal shock resistance, you have to have very low thermal expansion coefficient and at the same time, very high conductivity. So in this case, the Invar wins the day because it will be the highest thermal shock resistance that has been discovered. Now, another question, what would you think would be the lowest thermal shock resistance of all materials? An example. Well, if you think about it, we'll see that you look at ice. And ice, in this case, ice has a pretty high thermal expansion coefficient. And at the same time, it has very low strength. So that ratio is the opposite to the Invar, and therefore any small temperature gradient on an ice sheet will crack it. And that is illustrated here in this example. So if you look at Invar, it's about 10,000. If you look at ice, is even like close to 1. So that's a huge range between the ice and the Invar. So the ice has very low strength. This is strength ratio, by the way, this ratio of the strength to the elastic modulus. So in Invar, this ratio is 2 times 10 to the minus 3. For ice, it is 2 times 10 to the minus 4. So the ratio of the strength is pretty big, and at the same time, the linear expansion coefficient of ice is maybe 1, 2 orders of magnitude greater than the invar. So the ice is getting it from both ways, low strength and higher expansion coefficient. The method of cooling is important, and I wanted to talk a little bit about this. So if you consider one section, 1 centimeter section, and by the way, most thermally stressed materials are going to have their sections will be small, less than 1 centimeter, maybe half a centimeter or less. So if you consider 1 centimeter and cool it, then we look at the range of conditions. If you use slow air flow, the heat transfer coefficient is 10 units, is watts per meter square K. So this is considered small. If you consider fast water quench, this is liquid and quenching fast, then the heat transfer coefficient is the highest, it's 10,000. So in between these two conditions, you can have radiation cooling equivalent to about 40 watts per meter square K. Fast air cooling, you have about several hundred watts per meter square K. Like the turbine blade, for example, the heat transfer coefficient is going to be several hundred. Maybe if you do roughening and other methods of cooling, jet impingement, you can improve on that, but this is typical. And then the water is much higher because it has more heat capacity. So if you look at the different materials, foams is BU number is close to 1 because it doesn't conduct very well. So it's a BU number. You have to have very fast conduction to get it to be low. So metals are very low BU number here, and the foams are the highest, and the ceramics and polymers are in between. The next property that we will consider is the strength temperature chart. And the strength temperature chart is important because in all of the applications that we are considering, we want to have alloys or materials of the highest possible strength at the highest possible temperature. And as I showed you in the previous lecture, as the temperature increases, the strength of the material generally decreases. It's kind of a canonical behavior for all materials and alloys. We can have exceptions. We can work hard to alloy the materials and so forth to increase that temperature range. But generally, the higher the temperature, the lower the strength of the material, and we have to take that compromise. So the relationship between the strength and the temperature is important, and Ashby summarized this for all materials here in this chart. So it shows the strength now is an absolute value in megapascal. Note that it is logarithmic, so this is 10, 100, and 1,000. That's kind of the engineering range that we would consider. And the service temperature is going to be 30, 100, 300, 1,000. And then this is beyond 1,000. So if I consider our high temperature applications, I need to have materials that work in this range here, which means that we can use non-technical ceramics. That's not going to work for most mechanical applications. Bricks and stone and concrete are not going to work. Therefore, we consider ourselves only confined to technical ceramics like aluminum nitride, boron carbide, silicon carbide, alumina, silicon nitride, all of these here. They have a pretty high temperature range. They go all the way, but their strength is not very high. Or I can consider alloys, and the alloys are a little bit off, like the tungsten is in between, it has high strength and a high temperature. But then as you go to steels, you get lower temperature capability, nickel alloys, titanium alloys, and so forth, like we explained before. So you're moving backwards in terms of the temperature range. So the considerations we have will be between technical ceramics and refractory metals and high temperature nickel-based alloys. While you can see now these alloys, magnesium, aluminum, copper, and so forth, they might have some reasonable strength, but their maximum temperature capabilities is quite limited in here. In this case now we have seen that our discussion on material selection is complete. We have reviewed roughly all of the material properties needed for high temperature, and it's up to you now to go and further your education and look in real literature of the exact conditions of the material and the properties that are used in the design. And before you do your design project, I would like you to consider Ashby charts, and you make arguments based on these charts, what materials you would be selecting for what reason, either transient or steady state, or the level of the heat flux that you want to have, or the maximum operational temperature that we would consider, and so forth. And with that, we will conclude our lecture for today.